Hey everyone, welcome back to the lab. In this video, we're going to be talking about how fast we can sort 40,000 elements in a list in TypeScript. Now I'll talk a little bit about why we're doing this in the first place, but I thought this was like kind of a fun experiment, and so thought it was worth kind of sharing the process. So basically over the past few weeks, I've been interviewing for software engineering roles, and if you've done this before, you know they kind of like present you with a kind of real, like mostly hypothetical situation, and you try to come up with a reasonable solution given the constraints. And so to give some kind of context on why we did this, I was in an interview question, and basically they gave me a problem where we had a corpus of data with a cardinality of about 40,000, and then they were going to stream updates that basically needed to update the counts or the weights, I guess, associated with each of these pieces of data. And what they wanted you to do is to return the top 10 elements by count on read in an efficient manner. Now, when I dove into like the constraints a little bit and what this thing was actually going to be used for, it came out that there's only going to be a max of 5 users hitting this API endpoint, if you will, to read it. And they were going to be using this in such a way that they're only looking at it via a near real-time dashboard that you could imagine as like long polling like once a minute. And so the data actually could have a pretty long latency of like a minute or two is fine for its like freshness. And so when you look at like business constraints, often like what you actually have to do is much simpler because software, hardware these days is actually pretty fast. And so based on this scenario, I was kind of like, well, if we really don't care about latency and we only have 40,000 elements, the simple scalable solution for this is to just like sort 40,000 elements on read, because we can totally do that within 2 seconds. And this is very simple, easy to optimize with like a cache. And then we don't have to do any weird like on write processing because this thing is basically never read anyway. And we can, use that memory or whatever else for other operations in the web server that might need it more. And so this is my claim. And now obviously this is a hypothetical situation. Like I would probably say, don't do this in prod, or like really think about other things in prod, because of scalability reasons, though cache probably works pretty well with like a 1 minute TTL. Memory pressure, if you're like making copies of this 40K list and doing some sorts of things like that, you'd probably just use a database anyway, but we couldn't. And then, you might be blocking on thread if this takes like a whole second for every request. That's not great, especially if it's like a single threaded kind of environment, but all sorts of things why you probably wouldn't do this in prod if you had other options. But in this case, I think it was an okay solution. But I kept thinking about this and I was like, intuitively, I think we can sort 40,000 elements in TypeScript in less than 2 seconds, but I have never like actually done this because that's like a weird thing to do. So in this video, what I really want to, dive into is answering that question. Can we sort these 40,000 elements in TypeScript in less than 2 seconds over a range of different possibilities? So, different data types that you might see in maybe a web server environment, and then also different data sizes to kind of see like where the drop off might be if it exists for actually building a solution like. And so the executive summary, the answer is yes, we can totally sort 40,000 elements easily in less than 2 seconds. Of course, all those caveats we talked about before, but this is totally possible. The median in my benchmark runs is about 300 milliseconds, and the max that we saw in these runs was actually also about 300 milliseconds, which is way below the 2 second, constraints and latency that I kind of like set out for myself for that assumption. Now, in the rest of this video, I really want to dive into the specifics of this benchmark and how we got these numbers, because, all benchmarks have asterisks. And so I think it's important to kind of explain what those might be before you kind of just take this result for granted and the source of truth. So we're first going to start with just like the overall setup of these benchmarks so you can kind of get an idea of what we're doing. Dive into a little bit more of the results and specifics, especially for different data types and data sizes. And then we're going to talk about the code itself that runs the benchmark, because if there's a place for error, I'm pretty sure this is probably the source of it. And this will give you an understanding of how to run it yourself as well. We'll leave you off with some next steps, but for now, let's get into it. All right, first, the benchmark setup. So the first principle that I wanted to do was kind of cover various scenarios and kind of a best effort case. Like there's obviously infinite cases of different data types you might have and stuff like that. But I thought we could do probably an 80-20 here and just cover some very simple types, which covers most of scenarios. And so those are just going to be a simple number list. So just a list of a bunch of numbers, a list of a bunch of strings. And then I wanted to look at, a common thing. If you're building web servers or something, you'll probably have types. And so this will be some sort of object that has a property on it. And so we did an object sorting by its number property, and then an object sorting by its string property. And then I wanted to do a range of sizes from 10 to 100,000, just to kind of see what the results were. If you're going into the millions, like this is definitely where it seems like you probably don't want to do it in memory. But, again, given some of these results, maybe that's actually okay on today's hardware. The next kind of like principle I wanted to look at was to try and do this in a way that's uniform and reproducible based on hardware. I look at a lot of benchmarks around the internet, and one of the big asterisk I see often is that they're kind of just running this on their machine, and there's so many different kinds of machines out there. There's all sorts of different things running on the machine. Like some people are like, oh, I was running Diablo while I did this, so therefore it must be much faster. And it's like, well, I have no way to reproduce that. So I wanted to find an easy way to make this super reproducible, so anyone can run this and change the benchmarks and see what happens. And so for this, I just chose the Replit basic instance. It's free. Theoretically, it just runs on a random machine everywhere, so it's uniform. And I think it's really simple to set up, so hopefully that encourages people to actually do it a little bit more. The template we're using is just the official TypeScript template from Replit. I think this is just Node, though I'm not sure which version it is. It just gives you a half vCPU, which, I guess, what does that even mean? I don't know, but theoretically uniform across tests. 512 megabytes of RAM, and then has 1 gigabyte of storage, which is unused. If you look at these numbers and compare it to like a simple small instance, you might get AWS, Google Cloud, etc. It's relatively simple, so I kind of like this because it's kind of standard, but of course, probably results are gonna differ cross-platform because vCPU is kind of relative itself. Okay, and then the last kind of like principle or value or section I cared about was making simple benchmarking code. One, I want it to be self-contained and basically able to be copy-pastable, just so people understood what it meant. They could reproduce this themselves in kind of whatever environment they want. The other thing I wanted was just this to be able to do many runs and then summarize over the runs, just to get a big enough population that we could hopefully get some kind of stat sig results out of it. And then the third one is I just wanted to write this myself. I've always been curious about like writing a simple benchmarking code. So that was fun for me. Though again, if there's mistakes, it's probably in here. We'll dive into the code more in the code section, but I think this is a good overview to see kind of how these results came from. Okay, on to the results. So I only pulled out the median times here, but the benchmark does spit out a lot more results. So if you want more full results, you can look in the blog post here. We'll just be looking at median times. And so basically we have the item count in the left column, and then the column headers are the type of sort that happened. And we can see that for most of these up to 40K, we're well below, 300 millisecond mark. Up to even like 10,000, we basically have, it's not zero latency, but very low latency, like 32 milliseconds, well below like human perceived latency, which I think is like 100 or 150 or something like that. And of course at scale, this still is maybe too long, but still within 10,000, like it's very fast. When you get to 40,000 and 100,000, that's when things start to fall off. And so I think this is probably the edge of where you might consider doing in memory. But we actually see for a lot of these, it's still relatively low, below 300 milliseconds. So, who knows? Maybe if we looked at P90, it'd be a little bit worse and that'd be a better take, but still median's okay. And so one thing that I found here that I think was weird and maybe indicates something's wrong with the benchmarks is if we actually look at the sorting just primitive numbers, it actually performs worse than sorting strings, which is weird to me because I thought strings would have some overhead versus numbers, because maybe you could like bit shift numbers or something like that. And then it's also longer than sorting an object by a property which has a number on it, which really doesn't make sense to me because theoretically it should be the same. So I don't know if this is like something weird and how JavaScript just basic sort works. They're doing some pre-optimizations that don't make sense at large sizes, or if the benchmarks run, but it does seem to indicate that something's weird. My first hypothesis was that maybe it was because I was running this first, that the runtime was like cold, and so maybe whatever was first would be biased and slower. So I actually ran the same thing again at the end, where theoretically the runtime must be warm because these just ran. But we actually got similar results. So I don't think it's that, but I am still worried about this. It might be a problem. So let me know if you have suggestions or hypotheses for this, because I'm curious. I would expect numbers to sort faster than everything else, basically. Okay, so that's kind of the setup and all the results. If that's all you cared about, you can stop here. But I did want to dive into the code a bit because I think if there is an issue, this is where it's going to be. And I also thought it was kind of fun to build a benchmarker, so maybe others would find it interesting too. So here's an overview of like the benchmark code that I wrote. I basically split it up into 3 parts. The first one is the benchmark timer. And so this is the thing that's actually running the code to be benchmarked and getting a date timestamp, a start and end, and then kind of determining what the time elapsed is. And we'll look at the code in a second. And we use this by passing it into a scenario. And so the scenario is the second part, which is actually the code to be benchmarked. But I wanted it to be self-contained to easily kind of be able to read the scenario. And so I actually allowed the scenario to set up its own data or do whatever it wants. And then it can just use that benchmark timer that's passed in to tell the external framework, like, what do you actually want to time? And so this is useful because like probably most scenarios need to set up data. Like in this case, we're setting up 100,000 items on a list, and it's not fair to count the list creation as part of the sort because that's not what we're actually trying to time. And so this allows the scenarios actually a lot of flexibility to tell us what they want benchmark. The third part of this is just the benchmark runner. And so this kind of glues everything together, gives a nice interface for actually running these scenarios. So you give it a scenario and then it's going to run n times. And then based on the n times, it's going to summarize all the the data into like medians, max, min, and it's, easily extensible to add other stuff as well, other summarization things. So if you want to look at all this code, it is copy pastable. It's all located at this blog post linked here. So you can look at that if you want, and we'll just kind of dive into each of these pieces and how it goes together here. So first is this benchmark timer. And as I said, it's pretty simple. All it does is it takes in a code to benchmark, which is benchmark code. And this is basically just a function that's runnable that returns void. And this means that it's like super flexible. You can basically wrap anything in a function and run it. And all it does is it takes a start timestamp, it runs the code to benchmark, and then it takes an end timestamp and just returns the time elapsed. So super simple. And now we look at a scenario. This takes in, the benchmark timer. And then again, here's that benchmark timer, what it actually is. It's just code to run. And this is one thing that I love about, functional programming and programming languages with good, type systems is we can make these really simple, powerful interfaces that's literally just like, hey, it's a function, you run it with this one thing, and now you can wrap all sorts of things in this and get all sorts of flexibility out of this very simple type. This looks a little complicated here and probably like hard to like think about how it actually looks, but we'll look at an example in a minute that I think will make it a lot more clear. The last part is this benchmark runner, and again, this is just kind of gluing everything together to provide a nice interface for when you actually want to run your scenario. So it takes in that scenario, which again is going to like set up its data, then run the actual benchmark. It takes in a number of times it wants to actually run this. We're just creating our little results thing and basically a wrapper on our benchmark timer so that it knows that when it has a result, it should push to a results list. Then we're just going to run the actual scenario, the number of times we want to run. We're passing in that benchmark timer that we have here that again knows that it needs to call back into our results list when it has a result. And then we're just going to summarize all of this just by iterating over the results. Really simple, not the most efficient, but it doesn't matter. This is outside the benchmark, right? So that's a lot of code, but probably hard to understand how it goes together. And so I wanted to give you an example of what a scenario actually looks like. So here we just create a list of the different kinds of links that we want to run. So the different types. And then for each one of these, we're actually going to run this run and log benchmarks, which is just a glorified wrapper on that benchmark runner code I showed you that just logs to console. Basically, we just give it a name. We're giving it the number of iterations that we would like to run. This is set to 200, I believe. And then here's the scenario code. And so we can see that all it does is it's just a function that takes in a benchmark timer, doesn't even know what that thing is. It just knows it can call it. And then here we're just constructing our data. And because this is outside of timer, this is, not part of the benchmark. It's just, you can do whatever you want here to set up your data. It's creating its string list. And then it's like, hey, I'm ready to time something. I want to time string list.sort. And so that's how this, so that's it. That's kind of the approach to this, the results that we got, and a deep dive into the actual benchmark code itself. I would still, recommend if you're curious about this or disagree with something to run the benchmarks yourself. All benchmarks do have asterisks, so this one probably has a lot of faults of its own. You can find all the code in benchmarks again at this blog post linked here, and I'll have it linked in the description. And if you're into performance and benchmarks and want to do more, I have a dive into F# and Giraffe and how I increased the web server performance for this benchmark by about 6.5x, so that might be interesting to you. And that's it for this video. Thanks for watching, and I'll see you in the next one.